key to creating a mission-first network is using a data model that empowers you to do that. And so when we look at what the Session Smart Router is able to do, is it's able to translate intent into configuration and outcome in a way that is beyond any existing technology. And that's all a byproduct of the secure vector routing protocol that we developed and have opened up as an RFC. And so as an example, let's say we have some mission requirements. And those typically are going to be some set of a who, what, and how. And so you have to translate those into the underlying network configuration. So we want to be able to allow these certain people or devices or systems, so that's your who, to be able to access certain applications and services, your what. And then when they do, here's how we want the network to behave and perform. And so that relationship is key to be able to actually translate into the configuration and network behavior. And today there's a very big gap between those requirements and how that actually gets put in place. And so this gap is created because the legacy technology data models are all focused around packets. They're all operating stateless at layer 3. If you're able to go higher up in the OSI model and keep context of the session statefully across the network, you're able to look at the status of the session as it traverses the entire network and convey its context across each network element. And so this is what we're able to deliver with secure vector routing. And the result is we're able to create a session-aware fabric, so essentially what amounts to a distributed stateful firewall across the entire network, and a data model used to configure that network that has who, what, and how directly in it. So let's take an example. So let's say we have some mission planners that are going to be deploying or modifying a specific application, in this case C2ISR, and they want to change the network behavior. They want to change how this specific application is going to be prioritized to make it more important than everything else, to change how it's going to be connected and routed, so which specific paths are going to be chosen, how we're going to enforce SLAs and QoS, as well as to modify who's allowed to access the application, so to ensure only authorized users and devices can do it. So this is essentially a core tenet of Zero Trust. And then to be able to do all these things in real time versus taking weeks to months to implement. And the way that we do this is really by looking at this in a new way. So what we have in this requirement is a who, so I have a set of authorized users and devices. We have an application, which is the what. And then we have a set of criteria about how the network should behave, which is your how. So the who, what, and how is inherent to the data model of the Session Smart Router and the secure vector routing protocol. And so the who in our data model is referred to as a tenant. And tenancy is assigned to traffic as it ingresses the fabric. And we're looking at the source of that traffic to determine tenancy. So things like the source IP address or subnet, the ingress interface or VLANs, and we can use these things in combination. And this creates what amounts to an ingress VRF or a community of interest. And so each tenant in essence has its own routing table. Then we have a what. So the what in our data model is referred to as a service. This is similar to what you might use for like an application definition. And so that service contains details about how it's defined. And this is where you're going to. So things like the destination IP addresses, subnets, ports, and protocols in use, DNS, DPI, TLS information can all be used to define a service. And within that service, there's an access policy, which defines which specific tenants are allowed to access it. And then the service links to policies that define the how. And so if a tenant is allowed to access a service, then the how is determined for each session and over the life of those sessions. And so the how is defined with two separate pieces, the security policy and the service policy. The security policy controls encryption settings, and the service policy governs the routing QoS decisions that we make across the fabric for that specific session. So what we have is a tenant, which is going to be attempting to access a service. The access is denied by default unless the tenant is within the access policy. And then if it is, we'll leverage the contents of the security and service policy to take care of the routing and the encryption. So with the key components of the data model in mind, how do we actually process a session? So here we have a couple of Session Smart Routers, and they're going to be peering with each other using secure vector routing, and they're going to create a session-aware networking fabric. So essentially what amounts to a distributed stateful firewall. And so when our source, our who, creates a session towards its destination, the what, we're going to evaluate that session because we're completely stateful. So we'll detect that a new session has arrived, and then we'll see the who and the what of that session. So who is the source? What is their intended destination? Does the who have access to the what based upon policy? And if it does, we'll then associate policies with that session based upon where they're going. So the specifics of the what that are going to define the security and service policies. And those are associated with each individual session. Then those policies will leverage the details that are conveyed by secure vector routing that's in the routing table to make decisions about how to properly get through the network based upon those policies. And so what will happen, say for example, if we have a service policy that says, I want you to take paths with less than 100 milliseconds of latency, secure vector routing will figure that out, and then we'll route the traffic hop by hop till we reach the last SSR in the chain of custody. And key to secure vector routing, it is both a routing protocol as well as the transport mechanism that we use to transmit the session across the fabric. So we use this in lieu of tunnel-based encapsulation since we're tunnel-free. And then when we get to the last SSR, we're going to make a decision about how we want to deliver that traffic to its destination, either preserving the original source and destination information or NAT and load balancing the traffic to the destination. So now that we've kind of seen how the data model is used, how it's in play in the actual creation of a session and how the session is routed, how can one leverage the Session Smart Routing data model to build a more effective mechanism to route network traffic and deliver essentially on those mission requirements? So let's take the example of the Navy's 5th Fleet. So on the left-hand side, I have some tenants. And so I'm going to start with a parent tenant, and then we'll look at the children, and then we'll start on the right-hand side with our services and see the parent services and child services. And so what's nice about the data model that we use is that both tenants and services are hierarchical in nature. And so this leads to a lot of capability about how we can actually control who's able to access what. And so within the 5th Fleet, we have a destroyer squadron, the Eisenhower, the Monterey. The destroyer squadron has a bunch of destroyers, and then each of those destroyers has different source users that are going to want to consume data. So for example, we have sensors that may need to initiate connections to a sensor receiver. We have this, the DCGSN machines that may need to initiate connections to other applications. On the Monterey, we have similar sort of thing. And then within the Eisenhower, we have kind of 3 main categories that I've defined. So one is around flight operations, right, which is really these DCGSN machines. We then have applications that are running on the aircraft carrier itself. So for example, sensor collection and then command and control. So in this case, the application that's running on the carrier may need to access things, outside of the 5th Fleet and send them data, for example. And then we have the air wing. And so we have all the different, pieces of that air wing. And then for each one, we can then break down the individual aircraft and even down to, say, the sensors that are on that aircraft and the flight computers and all that sort of stuff. And so these are your sources of traffic. These are your individual who's. And then they're going to be accessing some what's. And so that is defined as our services. So we have our external applications. We have the MOC, so the Maritime Operations Center. And we can see the carrier application needs to be able to talk to the MOC. And we have some more specific relationships where sensor data and command and control, where the sensor collection that's happening on the aircraft carrier needs to send that sensor data back to the MOC. And then on the 5th Fleet, this is essentially the applications running on the aircraft carrier have a bunch of different use cases, for example. So we could have sensor collection, where all the different sensors that exist on the aircraft and the ships need to be able to send data to. We have the DCGSN application that's running that all those desktops and laptops need to be able to access. We have our pre-flight applications, so the flight computers that are running within these aircraft may need to talk to that to get data that they require. We then have intelligence operations that may need to be accessed to be able to collect certain data. And so this creates a directional map of who is allowed to access what. And then we actually instantiate this not just in comments, but actually in the routing table itself. So let's take a quick look at that. So let's take a look at how the tenant service structure creates access and how we can visualize that. Here we have our enterprise, which is essentially the authority under which all of the routers and all the configuration exists. And so here we have a bunch of different parent tenants, and then we also have subtenants underneath of it. And so we can see there's the 5th Fleet, and we can see our destroyers, and we can see the relationship down to what they're able to access. So the DCGSN machine is able to access the 5th Fleet, and then the command and control specific application. And then if we wanted to look at the entire relationship, I can just say I want to look at everything related to the 5th Fleet, and we get this view. And so this view goes all the way down to the individual items of, the flight computer on a specific FA-18 as access to the pre-flight application that's running on the Eisenhower. Whereas the ISR sensor, maybe that's compromised. Maybe that sensor's had something wrong with it where we're going to block access to the sensor data collection, versus this other FA-18, we're going to allow it. So we have very granular control, as well as the ability to visualize everything that is going on within the network from a routing standpoint. So if we wanted to not look at the Fifth Fleet, but we wanted to look at, say, the Mach, let's clear this out and pull that up. We can see how that works. So we have the Fifth Fleet, the Eisenhower, we then have the carrier applications, and then we have sensor collection accessing the sensor data in the Mach, and then command and control accessing the command and control in the Mach. And so the really beautiful part about the way this technology works is it's actually in the routing table itself. So if you were to look at the normal routing table on any typical router, what you'll see is a bunch of subnets and next hops. And basically, if there's something going on and you ask someone, well, what's 172.18.00/16? What is that? They're probably going to have no idea. And they're going to have to go look it up, and it's going to be very difficult to understand what is that related to. And so if you think about how these large-scale networks are built, people make configuration changes, they add things, and over time, you get a lot of configuration bloat, but you don't want to touch it because you don't necessarily know what any of it actually does. If you look at the way that we do routing, we're using tenants and services. And so I can see, for example, here's all the different things that are able to access the pre-flight application. So we can see essentially that this specific tenant, if it is destined to this specific subnet over these TCP ports, then it's going to be said to be going to the pre-flight application. And then we can see exactly how that is going to route and which specific paths it may take. And in this case, it's going to be load balancing across all three different paths. And so this gives you the ability to actually see what's happening in the routing table in a way that you haven't been able to before. And this isn't just comments in the routing table. This is inherent to how the product functions underneath the hood. So we're using tenants and service as a core component of the routing protocol. And if you look at the RFC, you'll see more details of exactly how that we're doing that. And so what this allows you to do is, if we look at our configuration, for example, and we look at, say, an application, so we can go find our services that exist in here. And let's say for Intel operations, we needed to suddenly change the access and the service policy. We could very easily change the service policy and apply that. So the ability to perform large-scale modification for end-to-end routing and security and how you want to enforce QoS is an extremely easy thing for us to do, and to be able to do it at scale and do it in a way that essentially looks like your org chart.